Hello, my name is Isabela Castañeda, and this presentation summarizes our data analysis project on Flex, evidence number 2. We analyzed two datasets, dataset A, which included the machine stoppages, which directly affect Flex's operational efficiency, and dataset B that contains the results of the FBT test for Maytag Series Line 6. And these datasets relate to Flex's problem of reducing downtime and improving consistency testing. The statistical tools we use, we began with descriptive statistics to explore distributions, outliers, and variability. For the machine stoppages data, we applied k-means clustering using K3 based on the elbow method. And this grouped machines by behavioral patterns and allowed us to later build a predictive classification model. To handle the imbalance across machine categories, our teammate Jonathan introduced us to SMOT and trained a classification model. And for the Maytag FBT dataset, we used PCA to reduce dimensionality and identify the variables that explain the most variability in the dataset. PCA requires standardized data, and we selected components based on the eigenvalues and variance explained. To estimate statistical limits, we use bootstrapping with 95 to 99% confidence intervals, and finally, Monte Carlo simulation that allowed us to test encoder behaviors across thousands of random scenarios. Together, these tools allowed us to model reliability and define test limits and create predictive decision support for Flix. For the deep dive, I selected PCA because it was essential to understanding measurement variability in the Maytag FBT dataset, and it helped us simplify a high-dimensional dataset and identify which variables actually drive variation in the test results. The PCA process started with cleaning and standardizing the dataset. We kept only the passing units to build a stable baseline. Then we calculated the covariance matrix and extracted the eigenvectors. And the PCA revealed the components explaining more than 80% of the total variance. And using the component scores, we generated statistical limits that became the foundation for our defining fail and pass criteria. The limitations it has is that it assumes a linear relationship. It becomes sensitive to outliers or non-standardized data, and also it can be hard to interpret the components because it can mix with several correlated variables. The PCA in our dashboard was extremely beneficial because it revealed that the angles variables define a principal component, meaning that they behave like categorical groups. And this allowed us to generate angle-based limits and integrate real-time pass and fail indicators directly on the dashboard, as you can see in this video. Our main insights show that the encoder values are highly consistent, which confirms test stability. Angles behave like categories, simplifying limit generation. And the statistical limit itself reduces false passes and false rejects. And for Flex, we believe that these insights support better calibration, detection of deviations, and a transition towards a more predictive monitoring and quality control. As a team, of course, we have our areas of opportunity, but overall, we delivered all stages on time, distributed responsibilities clearly, and our KPIs included data cleaning efficiency, model accuracy, and the dashboard completeness, as well as that this project strengthened our skills in reliability analysis, modeling dashboard design, and as well as project execution with a real industry partner. Thank you.